Okay, homework 11 is a bit of a review. So what I'm going to do is go through each problem. This first video is going to cover 1 and 2, so we see we're sketching curves. We have a polynomial here for number 1, and we want to find asymptotes, critical points, points of inflection, intervals of increasing, decreasing, and our different concavity, convexity. Okay. So in this situation, we can say that we're probably not going to have asymptotes because this is just kind of a regular algebraic situation here. Then if we want to talk about critical points and points of inflections, critical points and also this increasing and decreasing in your max and mins, that's going to be your first derivative. And then points of inflection and your concavity is going to deal with your second derivative. So if we go over here, we have our first derivative. I recommend making a chart that looks something like this, and so that you can keep track. So here we have our original function. We find it has one factor here, so it's got a 0 at 0. And this bit here, so here we can see it's a quadratic. I put q just in case some of you feel strange about using the quadratic formula for something that's to the fourth. If we put in a q equals x squared, then we see we have this quadratic. And what we see under here is that we have 625, which is 25 squared. It's negative, but that's squared, so it goes positive. And then here we have the 4 times 3 times 60. That becomes 760, so you have a negative number, which means you're going to have imaginary roots, so everything else is imaginary. So we just have this 1, and we've got, if I put in a negative here, then I get a negative value out, and if I put a positive. So what this means for my function is that it crosses the axis, crosses the x-axis at 0, and in the negative range it's below the x-axis, and in the positive x's it's above the x-axis. Okay, then we can take the derivative here. Go ahead and leave that up. If I take the derivative, bring this is kind of the easy form, right? I bring that down, so I get 15, then I take 1 off, so I get 15 x to the 4th minus 75 x squared plus 60, and I can factor out a 15, and then I come to this situation, and that can be factored into x squared minus 4 and x squared minus 1. Both of those are difference of squares, so I can break those down more. So I see I have four critical points here at 2, -2, 1, and -1. So I have those 4 labeled here, and each one of those gets a 0, and that means that's going to be where my local max and mins are. So when I put in my other pieces, and so for example, if I put a -3 to this, I'm going to have a negative value here, I'm going to have a negative value here, I'm going to have a negative value here, and a negative value here. So 4 negatives, and gives me a positive. So here I'm increasing. Let's see, for the first derivative, positive means increasing, negative means decreasing. So I'm positive to negative. That means I was increasing, then I was decreasing. So this is a local max, local min, local max, local min. And then we can go on to the second derivative. So I had this constant drops out, same situation here, so I have 60 x cubed minus 150x. I can take out a 30x, so I can see that 0 is going to be 1, and then when I solve this, if you didn't notice, I didn't explicitly write it out, but I'm setting each equation equal to 0 and solving for those values. So here I have square root of, the positive and negative roots of 5 halves. So I have a 0 there, a 0 from this 0, and another one on the positive side. And I can do the same thing if I put in negative 2, I look at it and say, okay, that term is negative. This term is going to be, if I put in negative, and then this is going to be positive, because you've got 4 times 2, and then only minus 5. Okay, so that's negative times positive, so that's negative, and then I can do the same thing for these pieces here. Now in this case, relative to my function, my original function, the second derivative tells me if it's positive, then I'm convex, and if it's negative, I'm concave. So I can kind of get a feel for these pieces. And as I draw my sketch, I'd put in these certain values, and I know that as I'm drawing it out, I'd have a little bit of, I'd be crossing my x-axis. Here I'd be looking for a local max, then a local min, and kind of working that out. And we have something that looks like that here. And see, okay, you can see what my function is here. It crosses here, so these would be the sketches I put in. I'd cross here, I'd be looking for a local max here, local min, local max. You can see our other values. This is the first derivative. You can see where it crosses each of these points. That corresponds to our maxes and mins. And you can see where it's positive, that's where we're increasing, and where it's negative, that's where we're decreasing. And then we can also look at our second derivative. You can see this part where it's negative, that's my concave, and then at this point it becomes positive all through here, so this is my convex through here. And same thing again, all this region is negative, so that's my concave again, and then convex from here, starting here. Okay, so that should give you a pretty good indication of how to work through a sketch of a situation like that. Number 2 is very similar. In number 2, we're asked g of x is x squared over the quantity x minus 2. Now this is a good situation where we're going to have asymptotes. Okay, so clearly we can't divide by 0, so this 2, we're going to have a vertical asymptote at x equals 2. What you can think about asymptotes, because some people get confused, especially with the horizontal asymptotes, sometimes not at the extremities, but toward the, at the kind of center region, you'll actually cross what ends up being an asymptote, and that's okay. If you want to think of an asymptote as an approximation, and your approximation gets better and better as you go out. So in this case, as we get closer and closer to 2, our curve is getting more and more vertical. So we have a vertical asymptote at x equals 2. And then we also want to check for horizontal and oblique or slant asymptotes. One way to do that is we can rearrange this. We can actually do a division problem here. And if I try to do this in long division, then if I had my x squared inside and my x minus 2, and then I'd say, okay, what times that gives me x squared? Well, that'd be x, and then I'd have this extra bit left over, so then I'd do 2, and then I'd have this remainder here. So then what you want to think of is, as x gets really big, what happens? Now in this case, we have this x term, so this keeps getting big. So you can say you're not going to have a horizontal asymptote, right? It's not going to a constant. But notice this term here. As x gets really, really big, this term kind of disappears, right? Which means you have x plus 2, which is a line. So we have an oblique asymptote at y equals x plus 2. Okay. So as we get closer to infinity, we get a a line that does a pretty good job of approximating our original curve. Okay, so just like we did on number 1, we're going to kind of create our chart. My zeros here, as I put this in, of course, if I put in 2, it's undefined. If I want to solve for 0, I just need x squared to be 0 and then denominator not to be 0. So if I put in 0, that works out. So I have that. And then I check my points around it, and I find that it's a negative, negative, and then positive. Okay, I go ahead and take the derivative of that. I can use the quotient rule there for derivatives. And I come up with this. I simplify a little bit. And again, I find 2 places that this is going to be important. So at 0 and at 4. Okay, so I have 0 and I have 4. And of course it's still undefined at 2. And then I find the pieces around it. And then when I take the second derivative, I get this big long mess, but that simplifies nicely down to 8 over the quantity x minus 2 cubed. And so this is still undefined. This is a constant, so it's never going to 0. So we don't have any 0 points. But we find less than 2 is going to be negative. That means it's going to be concave. And greater than 2 is going to be positive, which means it's going to be convex. And we can check our function here. So you can see we have our function that looks like this. I'm going to show you that this function here is the same as this. I've done my division through, and you can see that those cover the same portion. Okay, and then just to show a few things, we can see that that's my vertical asymptote. You can see as I get closer to it, it becomes a pretty good approximation for it. And then here's my oblique, and again you can see as we go out, our approximation gets better and better. Alright, and here we can see this situation where we have our first derivative. So where it's positive, we're increasing. Where it's negative, we're decreasing. So you can see how that follows. Over here, we're negative again, so we're still decreasing. And then we are increasing there. And we can also look at the second derivative, and you can see it's always negative over here. You can see our original curve in red, that we're always concave, and over here we're always convex, and it's always positive. Okay, so that gets us through problems 1 and 2, and for problem 3 we're going to have a similar situation. We're going to talk about it in the next video.